Okay.
Good. Okay. Apologize for those who I was recording this for. The only thing we talked about so far is just defining what an exponential function is and how we go from here to look at its inverse, which we call the logarithm, right? So I'm going to kind of write down the logarithm function in general, which is, so y equals log base a of x. So whenever I write this statement, I'm basically saying a let's see, if I want, so if the power that I take a, that I, or take, usually the word is raise, that I raise a to in order, I want to write 2 again, that'd be, in order to get x is the power y. Okay, so this is kind of whenever we talk about logarithms, I'm saying the power that I need to raise a to in order to get x is going to be the power of y. Okay, I want to make sure this is kind of cemented, that we understand this before we kind of just continue to work through our rules, right? So in each case, a logarithm is basically an exponent, right? We're dealing with an exponent. I'm seeing all the different exponents that I get that will happen if I want to take a to get some specific x that I've chosen. Okay. So this leads us, so maybe let me make a more general statement here. I'll probably just write this from the book for everybody. So the definition in general says if a is greater than 0 and a is not equal to 1, then log base a of, I'll use x here, equals y if and only if a to the x, a to the y in this case, equals x. Okay, so these are saying the same thing. Okay, so if anytime I'm dealing with an exponential equation, there's an equivalent kind of logarithm statement that I can use for it instead. And if I have some sort of logarithm statement, then there's going to be some corresponding exponential statement that kind of makes sense of it for me. Similar to how it was with the trig functions, right? If I had, you know, y equals the arc sine of x, right? This was the same thing as saying that the sine of y will give me the x, give me x, right? So this is where we're coming from when we're doing this. And there's a couple of example problems that are in the book and that I'll do here real quick, just to kind of illustrate this point, right? So let's say that I have 3 squared equals 9, right? But I want to write this in terms of a logarithm, right? Well, according to what this statement I wrote here and kind of the example from earlier, so a in this case is 3, right? So I'm going to write this as log. So this is equivalent to saying log base 3 and then x, which x in our case is this 9. And this is going to be equal to y, which was 2 in this case, right? So this is saying that 3 squared is 9 is the same thing as saying the power that will take 3 to 9 is the number 2. Okay, both functions are important for us to understand both ways of seeing it, because sometimes we may not have a simple statement like this. Sometimes in order to solve equations and kind of understand the system, we need to look at the exponent more than kind of the output in a way. Okay, any questions so far on this? This is concept. I assume most of you have seen this before, but definitely want to be hammering in a lot of this to go through. So, okay, good. And we'll do, we'll just do a real quick example the other way as well. How about log base 4 of 16 is 2. Okay, so let's say I'm given this logarithm expression and I want to rewrite this as an exponential. Okay, what is my base? So what's a in this case? It's 4, right? Because that's the number down here. So we take 4. What's my exponent? 2. Good. And then what's my or what's the value I'm finding? 16. Good. So 4 squared is going to be 16, right? So these are equivalent expressions. Okay. So this is the definition of a logarithm. This is kind of what we need in order to kind of study it and work through it. Okay. So there's a few examples, and let's take a bit of time here now with our graph that we already have of 2 to the x power. Let's see what the inverse function looks like, right? So this is, so I'm going to write here y is 2 to the x. Look like there's any extra colors now, that's okay. Now let's study, so this was 2 to the x, right? Now let's take some time and do, instead of 2 to the x, we're going to look at the inverse function, which would be log base 2 of x. Okay, so, and we'll use basically the same set of numbers here, right? So, well, actually not exactly the same, because some of these won't work, right? Remember, what we're dealing with here now are exponents, right? And so this function is the same thing as y equals log base 2 x. But I can rewrite that as 2 to the y equals x, right? So let's recall, so we already talked over here, x, we cannot get to 0, right? We can't get an output to be 0, right? So if x is 0, does this make sense? No, there's no solution, right? Because I get 2 to the y is 0. There's no y that'll give me 0. Okay, so we can't do 0. Let's talk about 1 though, right? So if we have 1, right? I want 2 to the y to be 1, which is, we talked about earlier, is going to be 0, right? And this actually applies for any case. There's a little example in the book that they do. They say, interpret it, show that like log base a of 1 is 0. We can rewrite this to say a to the 0, 1, right? Just based from our definition of the logarithm. So 0 is going to be the value we want here for log base 2 of x. Okay, similarly we can do 2, right? So now we want, so when we're doing log base 2 of 2, right? We're wanting to know 2 to what power gives me 2. And what is that? 1. Right. You just take 2 to the first power, right? Similarly, if I took 4, right, we're going to have 2. Right? And then if I took 1/2, the power that I raised 1/2 to give me, or sorry, that I raised 2 up to in order to give me 1/2 is -1, right? So it's just kind of flipped from this picture. But what we're going to see is that that's going to give me, so we have the point 1, 0, we have the point 2, 1, we have the point 4, 2, we have the point 1/2, -1. And so our graph is going to look like this. Okay, which makes sense. We had a bit of discussion last week talking about how inverses are kind of over that y equals x line, and so that would be our graph. Okay, I don't think there's too many examples of necessarily graphing logarithm functions. But you need to know how to do that. So in that case, just feel free to use points, or you can use curve sketching once we know how to do derivatives. So that'd be great, right? Anyway, okay. With logarithms, actually, I'll ask any questions. More questions so far? Before we get to some of the rules, right? So with logarithms, we have a few properties, right? Let's see if anybody remembers them. So let's say I have two values, m times n, multiplying inside a logarithm. And I want to find the logarithm with base a of m times n. How can I rewrite this? Okay. Why is that?
Because you're basically multiplying the two products of the x's. Oh, I don't understand.
No, you're good. You're good. So let me kind of put in terms what you're trying to say. So these are in some way, right? The m and the n is a to some power. I'll just call it p maybe. And n is a to some q power, right? So if I did the logarithm of them individually, right? Or when I multiply these together, you get, this is going to be, if I do m times n, right? I won't do this for all this, but just so we can understand what's going on, is going to be a to the p plus q, right? Because I just take the powers and add them together. This is log. Okay. So the power of this statement is just going to be p plus q, right? But if we take log base a of m, that's p. Log base a of n, that's q, right? So that's also p plus q. So it works out. It's just because they're exponents, and so they function as you expect exponents to do. Okay. Similarly, we have log base a of m divided by n is log base a of m minus log base a of n for similar reasons. Okay. The final one, log base a of m to the, what power is it? Okay. Do I know this one? Happens to this one. So we take k outside, multiply to the front, times log base a of m. And again, m, recall, is some a to the p, right? So what is, if I have a to the p, right, and I raise it to the k power, what can I do with those exponents? You multiply them, right? If I have, so I'm not saying a to the p times a to the q now. I have a to the p and then raising that to the k. So I can just multiply these together. Right? So that would be this guy. But in this case, right, you're going to have k times log base a of a to p, which is p. So you have p times k. So it works out. Okay, so again, just another rule of exponents being taken in an interesting form. Okay, so these are our three rules of logarithms that we want to use, which are going to be very vital to us because, okay, we're going to be eventually taking the derivatives of these things. Of course, working with them algebraically makes it easier to kind of break it down as well. But let me ask this question, pose this question to you. I haven't told you what the derivative of this thing is. But how many of you want to take the derivative of this? It's going to be pretty bad, right? But everything in here is going to fall in nicely into one of these rules. So I can actually take this and break it apart, right? I'll do it with simpler examples so we can, and then maybe we'll come back to that one, okay? But these are going to be very useful. So when we're taking the derivative of this, I don't have to take I don't have to do the outside part and figure out what's going on in here. I can have a bunch of little tiny problems and then just add them all up together using our derivative rules we had from before. So let's do a few examples. We'll do an example of each one, and then we'll work on, we can maybe try our hand as this guy here to see what happens. And that's basically the whole section. So yeah, okay. So example of this guy. Let's say I have log base 3 of 9 times, I'll just actually. Okay. So it would be nice. So 3, I can definitely take 3 to a nice power to give me a 9. So I'd like to be able to work out that one. But unfortunately, it's multiplied by this x right now. So how can I rewrite this statement? And then this statement is the same thing as saying 3 to what power gives me 9, which is 1, right? Yeah, so exactly. This is the same thing as 2 plus log base 3 of x. Good. So this is pretty simple from here, right? So I've basically just taken a pretty simple log graph and just moved it up by 2, essentially in a way. Okay. We'll do an example. Let's do log base 5 of log base 5 of 25 over y. Okay. So again, nothing too bad here. If they're dividing, then I can simply take it and separate it out. But instead of adding, I'm going to be subtracting. And again, 5 to what power gives me 25? 2. So this is the same thing as 2 minus log base 5 of y, which we can't simplify this because it's just y, right? You don't always have, if you can simplify it, it's cool, but only if you can see something clear, right? Obviously, if this was 24, you don't have to worry about trying to do it because there's no nice power you can take 5 to get 24, right? Cool. Okay. Last one, then we'll take on this guy down here. Okay. So we'll do log base. Someone give me a number. I didn't even remember what number it is. 4. Okay, great. Log base 4 of 16 to the x. Actually, let's make it more interesting. 64 to the x. Okay. So what can I do with that exponent? Good. So by our third rule here, I can take that x and bring it down to the front. So I get x times log base 4 of 64. Okay. Now I did set this up so we can solve it. Anybody know what log base 4 of 64 is? Right? It's 30. Because this is the same question as 4 to what power gives me 64, which it would just be 3, right? So this is actually just the same thing as 3x. So it's funny that you have something that looks a bit complicated and it's just 3 times x, right? So these logarithm rules are going to be very important to us. Okay, let's tackle this guy now with all of them combined together. Okay, because I won't tell you for sure. I do every problem on the quiz and on the test next Wednesday. That you will have to know how to expand the logarithm. Okay, so pretty big concept here. So we'll practice this big one and hopefully be able to get the idea of that. Okay, so what do we have? What is this monstrosity I came up with here? Log of square root of x plus 1 squared times x squared plus 1 over e to the x times x minus 4 to the 3 halves. And as a reminder, this is all of this is inside the square root. Okay, So we're going to work at this one piece at a time, right? We're going to make our way down to the center of this. Okay. By the way, I should mention I didn't put a base on this, and that's okay. If I don't put a base on my logarithm, so I'll go ahead and maybe I'll write this top here. If I just have log of x, this is the same thing as log base 10 of x, or what we call the common log. Okay, because 10 is a pretty easy number to work with when it comes to logarithms. So we call that one the common log. Okay, so in this case, we imagine log base 10, although it really won't do a whole lot to change our problem. I could have put a here, it would all work the same way. Okay, so I need some ideas here. Let's even the starting point. Okay, yeah, there's a big square root out of all of it. How can I rewrite that square root? Okay. So maybe to separate my two parentheses, I'll put a bracket around the whole outside. So we have x plus 1 squared times x squared plus 1 over e to the x minus 4 to the 3 halves. By the way, I wrote e to see if I remember what it is. What is it? Just curious. I'll explain it, of course, when you do it. Not in this case. So e is just a number. E is a special number. Maybe for our case, maybe we'll write this as 10 for now. I'll come back to that. Okay, so we'll do 10 to the x power. Okay, kind of match with our logarithm. Cool. Okay. Now I have log of something to the 1/2 power. So what can I do with that 1/2? Good. 1/2 log of x plus 1 squared times x squared plus 1 over 10 to the x power times x minus 4 to the 3 halves. Okay. Now, it is true that I have a few terms that are multiplying and dividing. So there's technically a few options we can go with, right? But I want to try to do kind of the simplest, take the simplest route. Okay. So in my mind, this division being here, I kind of want to get rid of that. Okay. Do the division part first and work with multiplying later. Okay. So I have something on the top divided by something on the bottom. Now there's things multiplying in it, but let's just consider those as one term for now. Okay. So if those are dividing, how can I rewrite those? Subtract them, right? Keep in mind that 1/2 still has to be on the outside, right? So I have 1/2 times the log of x plus 1 squared times x squared plus 1 minus the log of 10 to the x times x minus 4 to the 3 halves power. Okay, it's a lot of terms. There's still a few things we need to work out here, but we just expanded it, right? Okay, good. Now what can I do to each of these terms? Right, so now we just have things that are multiplying inside of our logarithms. So now I can take those and add them together. So I'm going to have 1/2 times log of x plus 1 squared plus the log of x squared plus 1 minus log, and I'll put this in brackets for now, 10 to the x plus log of x minus 4 . Okay, so let me point out something actually, because this sort of makes me think about the quiz. When we were taking the second derivative of the third question, a lot of you forgot to distribute the minus sign, right? If I have something, right? If I'm subtracting something that has two different terms in it, right? So it was like the product rule. So you would do the product rule and you would get two different terms, right? I need to make sure that minus goes with both terms, not just the front term, okay? this is why I kind of wrote this the way I did to make sure we know that minus sign is going to everything. Okay, so I'm gonna have 1/2 times. Okay, now we'll simplify a little bit on this left side. Can I do anything to this log of x plus 1 squared? Yeah. So 2 log of x plus 1. Good. So that's from the third rule we have. Can I do anything to this guy? What do you think? Log of x squared plus 1. Anything multiplying, dividing, any powers we can take out? No, because these are added. Okay, if we have an addition inside the logarithm, you can't separate that. You can't do anything with that. Okay, and then here we're going to have minus. So we're going to have a minus with this term. What's going to happen to that x? It's going to go on front, right? So we have minus x times log 10, and then minus again. What's going to happen to this 3/2? Yeah. Can I do anything else to that x minus 4 in there? No. It's because it's adding or subtracting. So there's no rule I can use to do that. Now, if I have like x plus 1 times x minus 4, like we had over here, right? These were multiplied, so I can do it. But if it's only a term where I have adding and subtracting, I can't split this up. Okay. So from here, so real quick, we can simplify things, maybe multiply that 1/2 that we, yeah. Oh, okay, I thought you had a question. So from here, we just kind of multiply our 1/2 across. We have log 10 now, right? Reminder, log x is the same thing as log base 10 of x. So what is the log base 10 of 10? Just 1, right? Because, so log 10 is the same thing as 10 to what power? Gives me 10, which is 1, right? So this ends up being 1. Okay, so I'm just left with x there. In the end, I take my 1/2 and I multiply to each term. So what's 1/2 times 2? So we get log of x plus 1. It's just 1 on the front of this term, so I get plus 1/2 log squared plus 1. Okay, 1/2 times just x. And then 1/2 times, what's 1/2 times minus 3/2? Okay, so this would be my final answer. Okay, so the question in this case would be to take the logarithm and expand it out as far as you possibly can, which this is the far as we can expand this on. Okay, so this statement is the same exact thing as this statement. Okay, nothing's changed between the two. Okay, but that one's more manageable for sure. I mean, you have a few terms to deal with at each point, right? But they're just adding or subtracting, so I can really just like look at it individually instead of having this whole mess of things inside the logarithm.
Then it's all being all divided by absolute.
No, you can take the negative can distribute, right? Essentially what happens, so if I want to combine this back together, right? I take the power of the pack enzyme first, of course, but then these would come together and be multiplying. And then you can divide each individual term. So I can divide this guy and then divide that guy. So no, it doesn't have to be parentheses to denote it. You can just multiply the negative each term. Okay. Any other questions on that? Okay. Good. So a couple other things I want to mention about the logarithm. One that's going to differ a little bit from the book, because I don't really like how the book kind of phrases the derivative. So I'm going to remind everybody of a rule that we have with logarithms. So we need to think about something called change of base formula. And this says that, so the reason that I had changed this to a 10 is just because that would be easier for the sake of the problem. If I left it as E, you know, there might be, you're gonna have like a conflict there that you can't necessarily resolve. And so that comes into play when we're dealing with logarithm or dealing with the derivatives of our logarithm. So something we need to use occasionally is something this thing called the change of base formula. So let's suppose that I have a logarithm, log base A of B. But I say I don't like base A. That's the worst base I could possibly think of. I would much rather have some other convenient base. Okay, and I'll call that base C. So I want to change this to a base C. The way that I do that is this logarithm is the same thing as log base C of whatever the argument is, which in this case, the argument's the thing that the logarithm of the base is being taken to. So B over log base C of hopefully many of you are familiar with this well. I've seen it before at some point. But what this says is that I can take any logarithm and rewrite it as the division of two other logarithms, right? So for example, if I have, let's say that I'm, you know, it's not gonna be a nice number. Let's say we have log base 3 of 4. Right? Well, I know that I can evaluate 4 in log base 2, or maybe we don't go that route. I like common logarithms better. You'll notice that if you use a calculator often, they don't have buttons for just any A, they only have a common logarithm button and what's called the natural logarithm, which I'll get back to. So let's say I want to write this as the common logarithm, which is log base 10. The way I do that is I'm going to write log, which is log base 10, of 4 over log of 3, right? So now this is just a division of simpler logarithms I can plug into a calculator and figure out. Okay, if I don't have a button to do this, right? So this is called the change of base formula. So you might play around with this. The book doesn't have any problems on this because it doesn't show it. But when it comes to getting the derivative, it's going to be a lot easier to have this to explain what's happening. Okay. And finally, I think that so they kind of have the last example they have in this section is basically just solving an equation, right? So I might just real quick demonstrate that. So the example they give in the book is 2.79. The x is going to be 4.68. Right now, you may have done examples in the past and in a class beforehand where you would have had a lot. You could have done, if I had 2 to the x power, right, equals 4, this would be pretty easy, right? Because what you do typically is, if they do share a common base, I can rewrite 4 as 2 to the second power, right? So then I can compare the exponents since the bases are the same, and that works. However, I would invite anyone to try to get these as a common base of some sort, right? Notice in this example, we only had to stick with exponents, and we can see that x would have to be 2. But in this case, it's a lot more complicated. So to get the actual number in this case, we need to interpret this using logarithms, right? Which you can either just use the definition that we had on the board earlier to rewrite this, or again, if we just try to rewrite this using that definition, you would get something like x is log base 2.79 and 4.68. We definitely can evaluate that in a calculator typically. So this is not going to be our way out. The way that we do this, right, kind of comes back to this change of base formula idea. I want to use common logs or natural logs, which again, also we'll get to work out this expression. So logarithms is a function, and as such, if these two things are equal, then I should be able to take the logarithm of both sides, and that should be equal, right? So what happens to this x if I take the logarithm? Goes down to the front, right? So we get x times log of 2.79 equals log of 4.68. So then what's x going to be in this case? Good. It's simply so these two things are multiplying now, right? So just take it and divide it from both sides. And so we get this, right? Now the answer we had when we did the exponential form, using change of base, we can write it like this. So sometimes it's easier to think about just apply the log to both sides, bring it down, solve for x. We'll get this. Okay. So something to keep in mind, like if you're trying to solve an equation with the exponent. Okay. So that is 6.6 from a more logarithm point of view. So now let's take our discussion and pour it into derivatives. Okay, because obviously I want to understand the rate of change of this, right? That's what we're here for. We want to study the rate of change of these functions. You took this class specifically because you were really interested to know the rate of change of these functions, right? That's where you're here. Anyway, does anybody have any questions about anything up here at the moment before I continue on? Okay. Okay, so we have to find the derivative, right? And unfortunately, or when we were doing the inverse trig derivatives, right? We kind of had the trig function, so we could just do it with some implicit fun, playing around and get the derivatives. However, we don't know how the exponential function, how the derivative is asked. So we're going to need to go back to the 4-step process, okay, to find the derivative of the logarithm. Okay, so we're going to start out with the function y equals log base a of x. And I want to take the derivative of this thing. Okay. So we have some suggestions. What's the first step of the 4-step process? So we're going to substitute y with y plus delta y. We're going to substitute x with x plus delta x. Okay. What's step 2? We're going to subtract the y, which it'll just be the y will be gone from this side. And I'm going to subtract y, which is log base a of x from the right side. So log base a of x plus delta x minus log base a of x. Okay, good. Let's see, is there anything that I can do with what I have here? Typically at this stage, we like to try to see if we can cancel anything. Here's an idea, because in this form, it might be a little weird to get kind of work out our limit in the future. What do we know about the difference of two logs that stay the same base? Aha, yes. It's the same thing as log base A over M over N. So this is the same thing as log base A of x plus delta x over x, which is the same thing as log base A of x divided by x, gives me 1, and we get plus delta x over. Okay. So that might be helpful. Step 3. What's step 3? Divide by delta x. So we have delta y over delta x. And then I'm not going to necessarily write delta x below the whole expression. I'm going to write it in front. So we have 1 over delta x times log of 1 plus delta x over x. Okay. Good. So we think, can I take the limit of that and just get it really easy?
Yeah.
Okay, so we really can't, right? Step 4 would be that I take the limit as delta x approaches 0 of this expression. But we're still missing some components here. There's really something I still can't tell about what's happening with this expression on the right side. Okay, so you know what that means? We're gonna have to be a little tricky here. So to get something to pop out. So that's exactly what we're gonna do. Okay. So I'll start writing over here. Here's the idea. What I want to happen is obviously there's not a lot that I could necessarily say about the logarithm expression of itself or take the limit of this thing. But if I can somehow push a lot of objects in here and look at that, I might be able to say something about it. So what the book does is it says that, so I'll do this. I'm gonna ask if this okay, right? Can I take this expression and multiply it by x and by 1 over x? Why? Right, you're just multiplying by 1, right? You don't have to understand why, you know, where you get the idea from to do that. A lot of times when it comes to the proof of these things, what happens is that you have mathematicians that experiment for a long time and try things out. And then when they write down their formal proof of the thing, you just see this, like you just see them putting it into it. But there's thought into it, but of course, a lot of that thought is above the scope of this class. So for now, just trust me on this point, that multiplying by x times 1 over delta 1 over x is going to help us. Okay. Now, what's going to happen is I'm going to have, I'll leave that 1 over x out in the front, and then I'm going to get x over delta x. So I just multiply the x with the x over delta x term. Log 1 plus delta x. Okay. Now, what I was saying before, right, is I want to try to not necessarily study what's happening outside with the logarithm term, which I forgot to put the A on here. But I want to kind of bring everything inside. So I'd like to bring all the delta x stuff inside. Okay. So if I want to bring, let's say I want to take this whole thing and bring it back inside. What would I do? You make an exponent. Good. We have 1 over x times log base a of 1 plus delta x over x to the x over delta x. Okay. So now this is our expression. So if I bring that over here, I'm going to have the limit as delta x approaches 0. So what I just wrote there is the same thing as this, as 1 over x times log base a of 1 plus delta x over x to the x over delta x. Okay, now, I don't think we really got to cover this point, right? But let's remind ourselves of the rules of our limits, right? So limits, if I have two things multiplying, I can take that limit to each one, as long as it exists, right? I promise you, I mean, there's no delta x here, so this one definitely exists. It's just 1 over x. And I promise you this one exists. So we're going to work to figure out what it is, but it does, okay? So I can take that limit to each piece. What I can also do with limits is, we've kind of seen this idea before, right? So I'll demonstrate with a simpler example. If I have the limit as x approaches 2, let's say x plus 1 squared, right? This is the same thing as keep the square on the outside. The limit as x approaches 2 of x plus 1, right? Well, essentially, I can just take that limit and kind of phase it through inside because what the functions are continuous, they're nice, right? And the same thing happens, right? If you solve this, you'd say, oh, plug in 2. If you solve this one, you say, oh, plug in 2, and then I'll just square it at the end. It gives you the same value, right? Because that's ultimately what's happening in both cases. But in this case, our logarithm, we had the graph, right? It's a neat continuous function. So I'm going to take this limit. We have 1 over x times the logarithm a of the limit as delta x approaches 0 of 1 plus delta x over x over delta x. Okay, so I just took that limit inside the function. So now I'm studying this thing over here. Okay, we don't have the rules, and you're not going to learn how to do this in this class. It's okay. Can I erase this over here? I'm gonna give everything a name here to kind of help out a little bit. So we have delta x over x, we have x over delta x, right? Those are just inverses of each other. So I'm gonna give delta x over x a name. I'll call it h. Okay? Which means, of course, that x over delta x equals 1 over h, because I just flipped it, right? Now, let me ask, what is the limit as delta x approaches 0 of delta x over x? 0, right? The x's have a delta x in it, so it doesn't matter. The delta x goes to 0, so you have 0 over x, which is 0. Okay? But we just said that this thing is h. So this limit that I'm dealing with in here is the same thing as saying the limit, so I'll say just this piece, is the limit as h approaches 0 of 1 plus h to the 1 over h. A little easier to see, of course, it's the same thing. And this is actually, it comes in this form, or actually, no, there's also, I could have also said h was this thing, and you would get kind of things flipped around with the same limit. We actually have a value for this. This is the definition for a number. So, any guesses what that number is? E. Funny enough, this is the definition for the number e. As a limit as h approaches 0 of 1 plus h to the 1 over h, it should be e. Now, I'm sure for those who probably taken a pre-algebra class or college algebra at some point, One of the topics that's discussed is generally, maybe not all the time, but deals with kind of interest, right? So I'm saying that if I'm given this initial amount of money, right? So this is just to kind of explain what's happening here. R over N. But it's something like this. So this is an equation for interest. And it says that, so I have N, which is kind of divide over the year. So if I say monthly, it would be 12, yearly, it would be 1, biannually, it'd be 2, daily, it'd be 365, etc. Right? But you also had a form of this equation that said, what happens if you do it continuously? So it keeps happening. That would be if N approaches infinity. That equation was this, P to the RT. And the reason why, these are both the same equation, but we simply took a limit just like this one and took it as it approaches infinity. And that's why E pops out. Okay, so just a curious fact if you remember seeing that before. But this kind of boils in the definition where E comes from. Now E has more uses than that, of course, but that's the number E. Okay. So with that being said, this thing in here is just E. Nice. So this whole expression ends up being 1 over x log base A of E. There you go. So I'm basically just taking 1 over x and multiplying by a number, right? And this is the way the book leaves it. I don't particularly get that, or I think that's the best way to do that, because especially if you're working with a calculator, you're not typically going to want to do log base A of E. Okay, so what I'm going to do is appeal to this change of base formula, right? Because to kind of do something with this E, so I don't have to put it inside this other logarithm. Okay, now E, just like with the common log, also has a special logarithm that's associated with it. And I'll make this one bigger because this one's more important in my mind. Anytime I deal with log base E of x, this is the same thing as the natural logarithm, and it's written by as alpha. Okay. This is the most common logarithm you'll encounter. If any of you decide to further pursue mathematics in any way, shape, or form, none of the other ones even close. Maybe you'll do common logarithms, but generally, the natural log is the way we want to stay. And the reason being is because, which I'll get to, of course, because of this expression and other things, E always pops out some way. So having a natural log is going to make this neater, right? So let's take this and rewrite it using natural logs with the common change of base formula. So how would I rewrite log base A of E using natural logs? Yeah, good. So we're going to do natural log of E over the natural log of A. Okay, and that just comes from, so my base in this case, I named it to be C, right? E is C in this case. So I have natural log of B over natural log of A, which in this case is E over A. Okay, but natural log is log base E. What's log base E of E? Right? Anytime you have a logarithm, it's just that thing it's the base and the argument of the same thing. Just okay. So the natural log of E is just 1. So we get 1 over x times the natural log of A. Okay. How's that? Is that a little bit of depth there, but we came out in the end with something pretty simple. The derivative of log base A of x, which I'll write that up here, on the board. One over x times the natural log. Okay. And then if I want to take log base a of u, this is going to be 1 over u times the natural log of a, simply times du over du. Okay. Notice there's a pattern every time you see a u put in there instead of an x. It's literally the same derivative, except you multiply by the derivative of the thing on the end, right? So I wrote all the different u definitions, but realistically, you could just know the base ones and then remember the chain rule, right? Which says that I take, if I have something inside the function besides x, I do the derivative normally with that thing, but then multiply by the derivative of the end. Okay, so all the formulas are up there if you need them. But really, you can short the list. So please learn chain rule. Still a lot of people missing on the chain rule thing. So if I need to go over that again or anything, just let me know. I'm going to finish this with them, of course. Okay. Specifically, there's one kind of caveat to this I want to mention, which is there's one special case that's really nice, right? Because on the bottom there we have x times the natural log of a, right? What a would be nice, so that I wouldn't even have that natural log part of the bottom. Not 0, we can't do logs of 0, remember? Not 1, because that would make it 0, and we're dividing by 0. What is it? What do we say?
10.
Not 10.
-10.
Not -10, right? Remember, natural log is the same thing as log base e of x. So if we use e, yeah. Basically, if we want to just take the derivative of the natural log of x, over x. Okay, don't have to worry about that silly little natural log of a at the bottom. It's just 1 over x. And then the chain rule would be 1 over u dx. Okay, that one's very important. And to reiterate that, I'll write all this for the people online as well. I'll use this change base formula. Okay. If I have log base a of x, the derivative of this is going to be 1 over x times the natural log of a. If I have anything besides x inside the logarithm, it's going to be 1 over u times the natural log of a times du over dx. If a is e, which is the most common scenario, and I get natural log of x, then it's just going to be 1 over x. And then if I'm taking the derivative of the natural log of u, it's going to be 1 over u. Right? So it's over there. For those in class, it's here. For those in class N, online as well. But this is our derivative. I don't know what it's like. 1 over x over it. Okay. Questions, comments, concerns? I'll probably practice a few derivatives of this. Questions? No? Yes? Maybe so? This is the big thing you want to remember here. Okay? If you missed everything I did over here, please remember these. Okay? Because all this work was to justify what we have here. Good. Okay. So let's go through a few quick examples of this. Example. let's first do log. We're going to take the derivative of log base 2 of x squared plus 1. Okay. So how do I take the derivative of this? Right. We need to go to our rules, right? We have log base 2 of some u, right? Because this is an x, this is u, right? So it tells me, right, the derivative of log base a of u is going to be 1 over u times the natural log of a. What is a in this case? 2. Good. Times du over dx. Good. That's it. Okay. Let's do we'll do the natural log of sine of x. Okay. How do I take the derivative of this thing? So we have the natural log of u. Okay. So what do I do with that u? Remember sine x times cosine. Good. The derivative of sine x is cosine x. Good. Right. This is, so this term is du over dx. Okay, that marks. So please remember 6.2 and 6.3 as well. That would be useful. Okay. So this is good here, but also this is the same thing as cosine x and sine of x, right? Yeah. So the derivative of the natural log of sine x is actually cosine. Okay. Now let's do another quick one. Log base 5 log base 5 of x plus 1 times x minus 3. Okay, what's my first step? I'm taking the derivative of this thing. Good. Let's split this apart. Okay. Because you could take the derivative of this thing as is, but you might run into a little bit more work than you need to. Right? So let's just rewrite this, split it up as log base 5 of x plus 1 plus log base 5. Okay. What's the derivative of log base 5 of x plus 1? So precisely our definition, right? And even in this case, so normally this is u, right? So we multiply by du over dx. What's du over dx in this case? Just 1, right? So we don't have to bother with it. Okay. What's the derivative of log base 5 of x minus 3? So that would be it. Okay. So to really demonstrate her point, well, I need some help here. Let's bring back our friend from earlier. Into the x times. Okay. So who wants to take the derivative as is? Raise your hand, anybody. Let's do it. No, I'm just kidding. If you did it, it would be the same thing, but let's expand it. So what's this as expanded form? So we get, what is it, log of x plus 1 plus half log of x squared plus 1 minus 1/2 x minus 3/4 log x minus 4. Is that correct? Good. So let's take the derivative of this thing. What's the derivative of log of x plus 1? Natural log of what's the base in this case? 10. Good. So that's that part. Okay. We already did this one, but it was for log base 2. So the only change is that it's log base 10 instead. So we have 1/2 times the derivative of that, which is over there. Except in this case, we're going to have x squared plus 1 natural log of 10. Okay. What's the derivative of negative 1/2 x? Okay. The derivative of negative 3/4 log of x minus 4. Now, was that so bad? So not. It's not too bad. You can simplify that a little bit if you want to, but it's I mean, I wouldn't say combine the fractions together. I mean like the 1/2 of the 2. No, please, you don't need to try to combine it together. Don't worry about that. Okay, but certainly if I split it up, that became a lot easier than what that problem would have been. Right? It's possible for us. We know how to do that. Let's figure it out. Okay. Any further questions? I want to make a statement real quick. I'm going to change the schedule slightly because I don't think it's going to take you long to go through exponentials. So I might go ahead and do Newton's method, which is the last lesson on Wednesday as well. And in that case, we can just use Monday as a review day. So don't worry anything. If that's okay. You are ready to go then. Let me know if you have any questions. Yes, yeah, you can do that. Yeah, I can do it. Yes. There's like a thing here and then you guys consecutive hours of action.
So it says solve the equation. Y cosine 3x.
So just like that. Yeah. Okay.
So,
Yeah, so how to approach this, right? So we want to solve this in terms of x, right? So the start would be, I need to get the thing with the x by itself, right? So I'm going to take, we'll move that 1 to the left side. So we get y plus 1 equals 2 cosine 3x divided by 2. Do you think? Sure. Okay. So here's the idea, right? I need to get this 3x part by itself, right? So whenever I'm trying to get something by itself, right? Normally we do, right? You did the inverse, right? Because here you added to undo the subtraction. Here you divided to get the multiply. So now we're doing the inverse of cosine, which is arc cosine. Remember, if I have y equals the cosine of x, this is the same statement as saying x equals the arc. Right? So in this case, y equals, this equals cosine 3x is the same thing as
X equals cosine of y.
so then x is, what's x gonna be?
Or cosine of y plus 1/2.
I'll leave that 1/3 out the front, but yeah, absolutely. So then your solution is gonna be. Now technically, does this say solve in a specific range?
No, it says solving equation for x.
So I would just leave this and that's fine. Technically, you might put a little a here because there's more than one option. Good, yeah, no problem. Thank you all for watching online.